smarter sensors, deeper pressure testing, and modular construction methods. Inside the fabrication hall, titanium rings are machined, inspected, coated, and assembled into circular frames. Curved glass panels are lifted by suction rigs and inserted into the ring grooves one by one. Each panel follows the same cylindrical geometry, slowly closing the round tube wall. Waterproof seals are compressed along the edges. Secondary anti-leak gel is applied around every glass to titanium seam. Circular end flanges are attached so that each tube segment can later connect to the next. Before a module ever touches the sea, it must survive pressure testing. The completed cylindrical glass and titanium tube is placed into a curved cradle shaped to support its round body. Pumps, sensors, test hoses, and inspection devices simulate deep ocean conditions. Engineers check for leaks, deformation, seal weakness, flange movement, and glass stress. Only after passing inspection can the module be transferred to a marine transport cradle and moved toward the dock. Offshore, the project becomes even more dramatic. Floating cranes, barges, survey boats, and underwater robots gather above the route. On the seabed below, anchor bases have already been prepared and protected by anti-scour rock. The first cylindrical transparent module is slowly lowered from the barge through the blue water. ROVs guide it with lights and robotic arms. The round tube hovers above its foundation, aligns with locking grooves, and descends until its support shoes settle into place. Hydraulic clamps secure it to the anchor bases. Crane cables are released only after the module is stable. Then the process repeats. Another cylindrical module is lowered. Its circular flange is aligned with the first module. Waterproof gasket rings are compressed between the two sections. The joint is sealed, pressure tested, scanned, and verified. One by one, the transparent tube segments form a continuous undersea corridor. From the outside, the structure looks like a glowing blue line running along the seabed. From the inside, it will one day feel like a passage through the ocean itself. But before passengers can enter, the tunnel must become a complete transport system. Emergency flood doors are installed at both transition zones, between the concrete tunnels and the transparent modules. Drainage channels and sump pumps are connected. Power conduits, communication cables, ventilation ducts, monitoring cameras, leak sensors, signal systems, and control networks are installed. The rail bed is built over vibration isolation pads. Steel rails are laid and aligned. Power rails are connected. Signal sensors are calibrated, and every system is tested without passengers. The first vehicle to move through the tunnel is not a passenger train. It is a small, unmanned inspection vehicle. It rolls slowly across the rails, passing over module joints and through the transparent tube, while sensors record vibration, alignment, power stability, and leak behavior. Only after that comes the empty trial train. It moves cautiously through the completed tunnel, proving that the rail system, flood doors, sensors, lighting, drainage, ventilation, and structural elements can work together safely. Finally, the construction atmosphere gives way to the passenger experience. Temporary guardrails are removed. Transparent safety barriers are installed. Observation platforms are completed inside selected widened modules. Blue underwater lighting runs along the titanium ribs. Glass surfaces are polished until the ocean appears clear beyond the curved walls. The tunnel is no longer just an engineering structure. It becomes a cinematic space beneath the sea. When the first passengers enter, they do not simply board a train, they step into a vision of future travel. On one side is the polished observation walkway, on the other is the rail line. Around them, the cylindrical glass walls reveal the deep ocean, small fish, drifting marine life, and the quiet blue world outside. A train glides through the transparent tube, its reflection moving across the glass and titanium rings. The journey feels both safe and impossible, realistic and dreamlike. This is the power of imagination when it is supported by engineering logic. Such a structure may not exist in the real world today, but it reflects a very real human desire to cross boundaries, to connect distant places, and to transform transportation into an experience of wonder. From the first seabed survey to the final blue-lit train moving beneath the ocean, this visionary undersea passage tells a story of ambition, precision, risk, beauty, and the belief that what once seemed impossible may one day become the blueprint for the future.